Assalamualaikum and good morning, Dr. Hairatul. We are from Group 30. We're presenting our critique of scientific literature on direct carbon dioxide mineralization using SWRO, which is seawater reverse osmosis brine and hollow fiber membrane contactors. For research background and problem, the article finds that desalination brine, environmental hazards, and carbon crisis are the factors that motivate this research. Seawater desalination provides essential fresh water, but it produces massive volumes of concentrated brine waste that harms the marine life if we dump into the ocean. At the same time, industrial carbon capture using traditional amine scrubber is extremely energy intensive and expensive. The main study objectives are integrate waste streams, maximize mass transfer, selective carbonation, and ensure stability. To solve both problems at once, this study proposes using hollow fiber membrane contactors to directly react the flue gas carbon dioxide with the divalent ions found in the seawater reverse osmosis brine. The main goals are to achieve high capture efficiency, selectively precipitate valuable carbonates, and ensure long-term operational stability using the lotus leaf-inspired membrane modifications. For experimental method, experimentally, the researchers fabricated highly porous polyvinylidene fluoride membrane and modified them with silane solutions to mimic the lotus leaf surfaces. They set up two membrane contactors in series. The first operates at a lower pH to selectively recover calcium carbonate, while the second operates at a higher pH to recover magnesium carbonate. For the key results from the study, we have two major keys. The first one is membrane stability and carbon dioxide removal. The membrane modifications were a major success. The lotus leaf-like surface structure prevented pore wetting and fouling, showing only a negligible 3.5% flux decline over 10 days of continuous operation. Furthermore, the system achieved up to 94% of carbon dioxide removal efficiency. The second major key result is selective mineralization. By using a stage pH swing, the process selectively separated the minerals. HFMC1 converted 99% of the calcium ions into aragonite, while HFMC2 converted 86% of the remaining magnesium into hydromagnesite. These solid products can be easily recovered through gravitational sedimentation. From an economic standpoint, the techno-economic analysis showed that this method cuts capture costs by 35% compared to the standard amine scrubbing. It also slashes the energy consumption by nearly 86% because it eliminates the need for the energy-intensive thermal gas desorption. Best of all, revenue from selling the carbonate products and carbon credits creates a highly profitable operation. For the article conclusion, this study demonstrated the first successful direct carbon dioxide mineralization using seawater reverse osmosis brine and advanced membrane contactors. It offers a brilliant dual solution that addresses both power plant emissions and marine brine pollution, all while delivering exceptional stability and strong economic viability.
Now we will continue for the clarity of the research question. This study uses advanced membrane technology to convert salty wastewater into solid minerals, simultaneously helping solve critical environmental challenges related to water desalination and carbon capture. The core focus is to test a new way to capture carbon using hollow fiber membrane contactors and salty wastewater. Instead of handling this problem separately, researchers use a controlled pH system with simulated brine to study how well the membranes transfer mass and capture carbon. The main goals are to achieve high carbon removal rates, turn calcium and magnesium into solid minerals without extra chemical pretreatment, and keep the membrane system stable and clean over a long period of continuous operation. Now for the appropriateness of the method. Number one is custom-led setup. The researchers built a logical custom setup using two hollow fiber membrane contactors connected in series. Number two, anti-wetting protection. They use reliable surface modification and pore-forming agents to create water-repellent surface that prevent clogging. Number three is stage pH swing strategy. Using a stage pH swings to capture calcium at a lower pH and magnesium at a higher pH to effectively separate different minerals. Number four is performance and cost evaluation. Combining physical materials tests with economic software ensure both scientific performance and financial costs are properly evaluated.
Now we will look at the validity of results and data interpretation. The study produced reliable results because the researchers used several analytical methods including SEM, SDE, and XRD to evaluate the HFMC membrane. They achieved 94% CO2 removal with 99% calcium conversion and 86% magnesium conversion. The authors also showed that the membrane design reduced fouling and improved performance. Overall, the results are well supported by the experimental data. For the limitations, although the study shows promising results, it has several limitations. First, the experiments were conducted only at laboratory scale. Second, simulated SWRO brine was used instead of real brine. Third, the membrane was tested for only 10 days, so its long-term performance is still uncertain. Finally, the techno-economic analysis was based on assumptions, so the actual industrial cost may be different.
Moving on to significance and ethics, this study by Li et al. Provides a major breakthrough by turning harmful desalination brine into a resource for carbon capture, achieving 94% of CO2 removal and cutting energy demands by nearly 86% compared to amine scrubbing makes large-scale mineralization far more economically practical. From an ethical perspective, it prevents severe marine damage caused by brine disposal while maintaining strong scientific integrity through detailed long-term testing and transparent economic modeling.
To conclude, this study provides a smart dual-purpose solution for carbon capture and desalination waste management. First, the surface-modified membrane solved the common issue of membrane wetting, achieving 94% carbon dioxide removal with almost no performance loss over 10 days. Second, using a stage pH swing, the system selectively recovers high-purity calcium and magnesium minerals as a useful byproducts. And finally, the economic analysis showed a 35% cost reduction compared to traditional amine scrubbing, making this a truly viable approach for industrial scale-up. And that concludes Group 30's presentation on direct carbon dioxide mineralization. As to say, innovations in carbon capture and brine valorization highlight the power of scientific inquiry in addressing global environmental challenges. Thank you very much for your time and attention, and that is all from our group. Thank you.